Hello everyone. In this video, you'll learn all about reinforcement learning, how to train ChatGPT, and build the world's best Go playing program. But let's start with something simpler. Remember Pong? It was one of the very first video games. The player on the left has a simple policy. It just follows the ball up and down. Let's train an AI Pong playing agent to compete with it. To do this, we'll need to define a policy that takes the state of the world as input and outputs an action, up in this case. As input, we'll take the ball X and Y positions and the two paddle positions. We'll also include the velocities, so our policy will get 8 inputs. To keep the figure simple, I won't show the velocities. We'll represent our policy as a neural network. Our network will multiply each of these values with a weight and sum them up. We'll add a sigmoid function to convert the result to a value between 0 and 1. If the result is larger than 0.5, we'll move up, otherwise down. That's it. Great, let's play some Pong. We'll start with random weights. Our random Pong player isn't very good. It just hides in the corner. This is like if you've never played tennis and you're matched against Serena Williams. You'd probably hide too. Or maybe you'd ask your opponent how to play. Suppose your partner told you exactly what to do for every step. We can use this kind of supervision to train our policy. Let's say our coach says to follow the ball. Here the ball is above our paddle, so the right answer is up. But suppose our network outputs 0.2, which means down. We'd like to change that 0.2 to a 1.0. Here's a different case where the right answer is down, and we'd like to drive the output to 0, a more confident down answer. We can accomplish this by defining an error function and optimizing the weights to reduce this error. Instead of numbers, let's draw these weights as colored lines. Positive weights are blue, and negative weights are red. Stronger weights have thicker lines. And the weights change a tiny bit after each optimization step. If we train on thousands of actions, the weights on the right start to converge. Now that we're trained up, let's play some games. Our Pong playing agent is pretty decent now, although it doesn't win very often. How can we train our agent to win more? Well, you can think of the game as a sequence of actions, which may lead to a loss or a win. Suppose we lose. We'd like our coach to tell us which actions were at fault. Maybe we messed up at the end. Then we could retrain our policy based on this feedback, as we've been doing before. Training a network like this is called supervised learning, and you need access to a really good coach. But suppose you don't have a coach. All you know is that this sequence of actions resulted in a loss, and this one produced a win. This kind of problem is called reinforcement learning. We don't know which actions were responsible, so we'll just penalize all actions we made in the loss, and reward or reinforce all actions we made in the win. This converts it into a supervised learning problem, just like we solved in the first part of this video. Actually, we can do a little bit better by penalizing later actions more, as the game losing the stake typically happens towards the end, and similarly for rewards. After training on 3,000 games, our agent has improved to play about as well as the opponent. You can see the score is pretty even. And after about 12,000 games, our agent figured out that hitting the ball with the corner of the paddle makes it go faster. Cool. And now it wins most of the time. Reinforcement learning is cool. You learn by trying stuff out, and sometimes you discover things that even the coaches don't know. But there are some challenges with this approach. Our neural network tries to minimize an error function. You can think of this function as a landscape, and we minimize it by rolling downhill, using an approach known as gradient descent. Gradient descent can get stuck in local minima, so we need to explore a wider range of policies to find the best one. So let's make the policy probabilistic. A 0.7 now means 70% chance of moving up, so the agent will actually move down 30% of the time. This bit of randomness allows our agent to get out of some of those local minima. To sum it up, here's the approach we've described so far. We'll start with randomly initialized weights. We then train with supervised learning and refine with reinforcement learning. Amazingly, we can skip the middle step and run reinforcement learning from random initial weights. It takes longer to train, but can still work for many problems. And we can do something even more amazing. So far, we've assumed the ball and paddle positions are provided as input to the policy. Suppose instead, all we had was a photo of the screen. The computer will see this as a bunch of numbers. It has no idea that this number is the ball, and these are the paddles. In other words, the policy has to learn not just how to act, but also how to see. It's helpful to encode velocity information as well. One way to do this is to subtract the previous from the current frame. Now positive values are from the current frame, and negatives are from the previous one. Instead of a 2D image, we'll stack all the rows into one long vector of pixels. And we'll connect all these pixels to a neuron. Now we'll add more neurons, 10 in total. We'll use rectified linear activation functions. These are pretty standard. They connect to a sigmoid neuron at the end, and it will output the probability of moving up. This may look complicated, but it's actually really small for a deep net. There are only 11 neurons in this network. Compare this to the human brain, which has billions of neurons in the visual cortex. How can you see with only 11 neurons? Let's train the network and find out. We'll start with completely random weights. It took about 6 million games to learn a policy that beats the computer on average. That's almost a week running on my MacBook Air. But what's this network actually learning? Does it really learn how to see? Let's examine the first neuron. It has a weight for every pixel in the image. Remember, these pixels form a 2D image, and each one has a corresponding weight. So we can visualize the weights as an image in the shape of the Pong screen. It looks like noise because I've randomly initialized the weights. The white ones here have the largest absolute value. Now we'll start training the policy by playing games. And you can see that it converges to a specific pattern after 1 million and 6 million games. These streaks correspond to ball trajectories that this neuron is attending to, and it's particularly interested in these paddle positions. It's also looking at the opponent's paddle, which is a good indicator of ball position. This is just one neuron. The others look for different patterns. So our simple network has kind of learned how to see. This approach to reinforcement learning is called policy gradient, and you can make it even better by limiting the size of each update in a variant known as PPO. Together they power many exciting applications. We'll talk about two of them, AlphaGo and ChatGPT, in the next two videos. Stay tuned.